Adrian works at Battery Ventures, where he advises the firm and its portfolio companies about technology issues and also assists with deal sourcing and due diligence. He was a founding member of eBay Research Labs, developing advanced mobile applications and even building his own homebrew phone years before iPhone and Android launch. You may also recognize him from his work at Netflix and his many cameos on the hit TV series Mr. Robot. Let's give it up for Adrian.
And we have, thanks Ines, pink champagne, excellent, that's a first. All right, so as Ines said, I work for Battery Ventures, and I look after portfolio companies. We have an office a couple of blocks from here, like all the other VC firms. And I also tinker around with some technologies, and I built some things, and I'll get to that. This talk is pretty much about how I ended up with the path that took me to tinkering with the latest things I've been playing with. And I like networking with interesting people. That's all of you guys. Thanks for coming. And I do lots of talks at conferences and advise people and a bit of consulting and things. And yeah. And one of the things I noticed, lots of stuff was written in Go. Like over the last couple of years, companies come in and they say, "Hey, we built this thing. What did you?" And the rest of the VC guys ask, how much they're selling and who they're selling it to, and all those sort of VC questions, and how much money did you raise? And I asked, "Well, what did you write it in? How does it scale?" And everyone's been saying Go. So Go's interesting because it's got extra stuff in it that is based on. People say, "Well, Go, well, it's based on communicating sequential processes and a bunch of stuff like that." So I'm going to go into some things that kind of lead up to doing more fun things with Go. And this is actually going to be communicating sequential papers, because I'm actually going to talk about 5 different papers. And here is the connection. This is the process diagram with the connections between them. So we start with CSP. That led to a thing called Occam that I'll go into, and something called Pi calculus in 1992. And then this thing called Occam-Pi that combined the two. And then there's a nice paper called The Life of Occam-Pi that came out in 2013. And somewhere before that, I actually did some stuff with Occam-Pi and wrote a simulator that I then rewrote into Go. So that's kind of that 2006 one's actually one I wrote, which is, I guess, cheating, doing your own paper, but whatever. So what is CSP? Here's the front page, and here's the sort of cool things about it. It does a whole bunch of things where it basically says, you can do a lot of stuff in programming if your building block of programming is everything is a process and everything else is communication between those processes. In fact, there are no functions in this language. In fact, it is non-functional programming. So anyone that really thinks that everything should be done with functional programming, this is the opposite. This is non-functional programming. Everything is a process and you communicate between the processes. But CSP said it should not be regarded as suitable for use as a programming language. That's a bit of a downer, really, isn't it? Like, okay, we have this great thing. You can't write stuff in it. There's no compiler for it. Oh, well. So this is the syntax in BNF. I colored a few things in red that you might make to show what's interesting here. There's input commands and output commands as part of language syntax. So that's different to most languages. Most languages don't have that. And then there's alternative, repetitive, parallel, and commandless, which is sequential. Most programming languages just have sequential, and maybe you have a few library routines that figure out how to start threads and library routines for doing I/O. Part of this language is an alternate command. An alternative command looks a bit like a select. If you're used to doing sort of, network programming in Unix, there's this select or poll, right? You're looking at lots of file descriptors, and the first one that does something is the one you get things from. So in Go, there is actually a select keyword, and it is also part of that language. Repetitive command is the for loop. That's pretty normal. And the parallel command means that built into the language is the ability to kick off more threads to go do something, right? The way you target the input and output is you mention the name of another process. So every process is named. Everything process has to be named, otherwise you can't send a message to it. So that's the basis of this language. And there will be a test. Are you ready for the test? Okay, so here's some code written in that. So I did warn you. This is, prime number civ, like one of those programming that everyone always puts in all their examples. This is a program which will emit prime numbers. But instead of doing it in the usual way, what it does is it creates a separate process for each prime number it finds, and that process is then you filter all the other numbers through that process, and it filters out everything that isn't a prime number. When it sees another prime number, it passes it on and creates another process. So this will give you all the prime numbers, the first 100 prime numbers. There's another issue in CSP, it doesn't allow recursion, which is fine as long as every machine has fixed memory anyway, so you just use as much memory as you want. Just set that number big. I colored it in, and just to make it a bit clearer, here's the architecture, like the process architecture. So what you've got is Civ 0, which is the second thing down there, the blue bit. And what it does is it prints 2, because 2 is the first prime number, but 2 is a fairly uninteresting prime number. It's just defined to be the first one. Really, it starts with 3, and then it only feeds odd numbers in, so because you know that even numbers can't be prime because they're multiples of 2, so there's no point checking, right? So you just feed 3 in, and then there's 100 Civ processes, which are in that, whatever, greeny color, and I sort of put the gap there. So they all connect together and pass things through. The first thing that gets passed is the first number it saw, which is the prime number, and it remembers that number. Then it filters out everything that's a multiple of that. And then finally, there's Civ 101, which does nothing but collect the final result and print it. So there's an initiator, a terminator, and a bunch of stuff in the middle. And then there's this print command, which just for 101 times will collect a number and print it, right? Now, the problem with this programming language is there's no compiler for it. So if you want to check that you've got your code right, you have to squint at it really, really hard and think really hard and use your brain to decide that this is probably correct. So there may well be bugs in this, but this is pretty much verbatim from the paper. So the CSP paper has a bunch of examples of things. Oh yeah, so the syntax here. Question mark is used when you're reading from a channel. When you want to send to a channel, you do an exclamation mark. Repetitive, they put a star around some brackets. Alternate, you wrap it in brackets, and any other alternates, you put brackets back to back in the middle, square brackets, which is a bit hard to see, but there's a double square bracket in the middle between skip and M. Parallel, you put vertical bars. So the stuff that's in black on this open bracket and the vertical bars, the closed bracket, that sets up the framework. That says start all these things in parallel, and then the different colors are each of the individual processes that are started. So that's the structure of this program. So a few issues with this. Like I've said, it's not a full language. It's hard to read, I think. And it's addressing things by processes. It turns out that actually makes it difficult to generate abstractions because everything always knows about everything else. And it's hard to build libraries and abstractions and ways to... You basically want to have some more indirection in the system. Now, I'm just going to move on. What is Occam? So Occam's razor is a nice piece of Latin, which I won't try and pronounce. But it basically means entities must not be multiplied beyond necessity. Right? It's basically the principle of simplicity, and it dates back to William of Occam, who was a monk or something back in the 13th century. So David May, in 1983, came out with this language called Occam, which is basically a very slightly extended CSP. It's very simple, very elegant, and it has this really excellent thing. The last line in the paper says, it's intended to be the smallest language, which is adequate for its purpose. However, suggestions for further simplification would be welcome. All right, and this was, I just gave this talk at GopherCon earlier this week, and this is like, you could kind of channel Rob Pike going, no, I do not want to add more things to Go, right? There's this idea that you want to keep simplifying things, and most people, when they see something, oh, I could add all these extra things to it. No, give me some examples for things to take away. The main thing it did was add named channels. So it's a little bit different from CSP. Instead of sending a message to a process, you send it to a channel, and the other channels read from that process. And now you can pass channels around between things. It is also a non-functional language. Here's the initial paper. It was actually a bit hard to get this paper. I ended up paying money to one of the services. It's not a very heavily cited paper, but if anyone wants to read it, I'm sure they won't mind if I share it if you really, really want to hear it. The interesting thing about this, though, the language was built for a reason. It was built because in early 1980s, they were trying to build microprocessors that were going to be connected together in large arrays. These were called transputers, and I, back in the mid-80s, was actually building things out of transputers, and as a side effect of this, I had to learn Occam, because it was effectively the assembly language for the transputer. So mid-80s, I'm trying to figure out how to program this particular new kind of hardware, which died out later on because it's an English microprocessor, and microprocessors are supposed to come from Silicon Valley, apparently. So I hadn't moved here yet. So this is a couple of interesting examples. Let's show you what this one on the left. First of all, it's indent-based structure. This is like a few decades before Python decided that was also a good idea. Definitions of scope. So it says var, that's a variable. And then the end of the list of variables has a colon, and that kind of binds it onto that next sequence. So that means that everything in scope of that sequence knows about those variables. So you put the variables outside the block, not inside the block, which is a little different, but you can kind of see why it needs to do that a bit later. And then there's this going equals true. While going, it's a loop, and you send it a message on the in channel, and it will delay for 100 microseconds, or whatever the unit of time is, and then send it on the out channel. So it's got an alt, and the alt is an alternative input. And one of the things it's inputting from is the channel in, gets a value. And then at that point, it takes now. Oh, by the way, all keywords are in uppercase. The word now is a keyword that returns the current time, because time is totally built into this language as an intrinsic part of the language, which is another interesting construct that I haven't seen very often. And then the next thing it does is to wait till after D. Well, I added 100 to D, so D is sometime in the future, and it can just wait till after that, and this thing will, that line in this code will become true at that point, and you will get scheduled. And then you output V, and then if you want to stop this thing, you have to send it a message, and it doesn't care what you send it, so anything can be read from the stop channel. That sets going false, and the next loop it stops. So it's a very compact, interesting piece of code here. It's a whole bunch of interesting things here. I thought it was really cool to have time built into the language, and Go kind of has time in the language, but sort of not really to this extent. The other one is a pipeline that looks a little bit like the Civ program that we showed you before. So you have a pipeline, you send something in the beginning, and it just chains the thing through. In this case, it just adds one to it. I want to make this the simplest possible pipeline. But it illustrates another piece of the language, which is the par command. Every line of code in a par command is a parallel piece of code. It gets run in parallel. So instead of saying the go routine thing you do in Go, we say go, 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 go on every line. You want to be a separate thing, and they all have to be functions. This thing just says any statement can be run in parallel with any other statement by just wrapping a par around it. The other thing that isn't obvious is at the end of the par, there is basically a wait group. If you're familiar with Go, you have these wait groups where you add yourself to the wait group, and you want to block waiting for everything to finish, you actually have to explicitly wrap a wait group around it. So the wait group is implicit in the way this par works, and it's implicit in the way that the CSP parallel construct works. You wait for everything to finish, and then you move on. The other thing that's in there is the iterator, and you can apply this I equals 1 for 100 type thing to any of the other constructs. So a for loop is sequence I equals 1 to 100. An alt input from lots of different things is an alt I equals 1 to 100, and you can create 100 parallel processes by just saying par I equals 1 to 100. So it's a very regular language. Now, I won't go into it in much more detail, but there's lots of cool examples in this, and one of the things about this language was designed to be programmatically modified. You could actually do program proving with this. You could actually come up with deadlock-free algorithms. You could transform your algorithms programmatically. So there was a lot of thought put into this language to make it possible to reason about the language on the basis that programming parallel is hard anyway, so we need better tooling around it. It's also one of the pickiest compilers ever, and it will not compile anything. Like if you get a variable and you use it from in two parallel threads, that's a syntax error. It checks that you only use things in one thread, and it will actually blow up if you try to do any. It's not possible to have a concurrent modification exception in this language. It's a compile time error, so it's very picky. So here's the Civ translated. I won't go through the details too much, but the interesting thing here is the naming has shifted from channels to the channels instead of the processes. So instead of having a process called print, I have a process that's actually not named. I just call it printer in the diagram to show you what it was. But actually, it's the channel that connects to it is called print, and then the other Civ channels, right? And this is called Eratosthenes, because Eratosthenes Civ, and it just outputs Civ prime numbers on its output. If you if you grab that, if you run it as this function, it will just keep returning prime numbers to you. Okay. All right, so that's all quite interesting. We've got all of these channels, we've got these processes. It's a fairly fixed structure, though. So let's look at pi calculus next. So in 1992, Robin Milner and his friends from University of Warwick in England, and various other places, in Scotland, England, and Sweden. Yeah. Pi calculus. So what's different here? The really interesting thing, this expresses processes that have changing structure. So previously we looked at connections of processes and channels and things with a fixed structure, and you create an algorithm with a fixed structure. Here, we want to start making this dynamic. We want to be able to send messages between neighbors that change the connections between all of their neighbors and all their other things. So this is now a dynamically connected network, and it has some relationships to actor systems, but it's sort of a little bit more fundamental. Now, the thing about this paper is they were trying to come up with a complete calculus, and at one point actually proves that lambda calculus, functional programming, can be implemented as a subset of process calculus without any functions at all, but just by sending lots of extra messages. Unfortunately, the algorithms, the stuff used to do this is incomprehensible, really. So this is probably the least readable paper, and there's 60 pages of this. And then there's part 2, which is even more pages of this incomprehensible, really it's gibberish. I mean, there is a syntax here, and if you absolutely stare at it, you might be able to figure it out. But then he says things like, and simple equations such as, and then you get the bottom line of that first block, which is, I have no idea. I mean, if I stared at it for an hour, I might figure it out. And then more generally, it's easy to show that something. No, I gave up. Luckily, you don't have to learn this. There have been a number of attempts to take the core ideas. This is a calculus that proves that. It's a series of proofs that show that you can do this. But you don't actually, as long as you believe the proofs, you can implement this in other ways. In languages which are easier to read, in fact. So Peter Welch is one of the sort of continuing people that still plays around with the Occam language. And this is a really nice, easy-to-read paper without lots of Greek and weird symbols in it, talking about the history of this stuff. And he talks at the history of Occam, the underlying philosophy, the foundation on CSP, the principles, and the development over 30 years into Occam-Pi, which is Pi calculus added to Occam. So all of this ability to do much more dynamic work with channels added to that very simple Occam syntax that we were looking at before. And there were a few other things added to Occam along the way. But this was an interesting thing. And at some point I knew Occam, and I kind of squinted at Occam-Pi and figured out a few things about it. There's 2 things you can do in Occam-Pi. Well, actually, there's the idea of mobile types. Right, and this is one of those things which, like, mostly it's a little bit of a brain stretcher for most people. Let's say I have x equals 1 and y equals x, and they are mobile types, mobile integers. X equals 1, y equals x. X no longer equals 1 once you assign. The 1 has moved, right? So you have 2 variables. If you assigned it to 1, and then I assigned it to this other one, the first one is now undefined. So x equals 1, y equals x. X is now undefined. It's an error to read it because it used to be 1, but you gave the 1 to somebody else. Right? So the idea of a mobile type means that you can pass things and know that you can't reference them anymore. It's a way to unreference things. Right? Now you can also have mobile channels. You can take a channel and you can assign a channel, and you can safely do this because you can prove that you can no longer write to this channel because you've assigned it to somewhere else, so you can't write to it over here. So you can safely reason about the channel behavior of this system. And the really weird thing is you can have mobile processors. So while a process is running, you can actually send it down a channel. And what actually happens is its stack is sent over the channel to the other end. And you can no longer run it here. You can continue running it somewhere else. So you can have pieces of code which are in mid-execution, and you can send their current execution state over a channel somewhere else and continue running them there. I never actually found a use for that, but it sounds cool. All right. In 2006, roughly 05, 06, I was working at eBay Research Labs, and we were building this peer-to-peer trading system using Skype as a transport, with the idea you were selling to your friends on Skype. And this is because eBay had recently bought Skype, and it looked like a fun research project. And this was actually published in an IEEE paper, so this is me cheating. I wrote this paper. But this is a quick summary of it, and you can see some of these mobile channels which are defined here. And this little process diagram, and that thing on the left that with all the dots is all of the little peer-to-peer things all chatting to each other. And I was using it to basically, as a protocol simulator, to explore fairly complex trading patterns and different ways. And I was trying to make sure that it didn't deadlock or live lock or have a concentration or black hole routes or nasty things like that. And you can kind of see the process structure is under that par, and there's a bunch of sequentials to set everything up. So this is the top level of the program. You define all the channels, and then you in parallel, you start all the processes. The dynamic bit was the connections between the nodes. Now, you may notice that the flexible simulation manager is illustrated by the flying spaghetti monster. And I'm very proud of the fact that I got a flying spaghetti monster logo into a refereed IEEE paper. And there's a bunch of noodles for connecting to the pirates. Anyway, if you're into nerdy physics jokes, that makes some kind of sense. So, just to wrap up then, pi calculus patterns can be applied to Go. So at some point, I decided that I wanted to learn Go, and I'd written this thing in Occam years ago, and I decided, well, why don't I try and rewrite that in Go just to prove, since it's supposed to be based on CSP, it must be roughly possible to do this. So I did. And there's a diagram with some more pirates all chatting to each other. And so I implemented the same algorithm. This is where I actually generate some interesting feedback. I won on Monday when I gave this paper. Rob Pike came up to me after the talk because I pointed out that every version of Go was getting slightly slower. So I said that I won at Pokemon Go, right? Because Rob Pike came up to me after my talk, and that was my big win on Monday. And then he found some other Googlers to come and talk to me about why this was getting slower, so they're going to fix it. So a lesson here, if you have an interesting performance problem and you tweet it and you get no response, like put it up in a conference where people are watching and they will pay attention to it. So there's a bunch of benchmarks and things here. So this is a little program which runs this flying spaghetti monster and pirates simulation. So that was interesting, but then I took that and I built a microservices simulator using this. And if you want to build interestingly large, complicated microservice environments, you can actually simulate it. And this is 100, by the way, I should explain what this is doing. This is creating 100,000 threads, 100,000 pirates, 100,000 of these nodes, and 100,000 channels. To initialize the network, it sends 4 messages to each. This is your name, a bunch of other things. And then finally, the fourth message is goodbye, go away again. And the 5th message is coming back from that pirate saying, okay, I've gone now. All right, a message received as an acknowledgement. So each message, if you just start up the simulation and shut it down immediately, there are 5 messages per process. So this is 500,000 messages. It creates 100,000 threads, sends 500,000 messages, shuts down 100,000 threads, and does that in 2.5 seconds. All right? So it's about 200,000 messages per second, except it got slower, and now it's like 3.6 seconds. So that's obviously way too slow. So I'm using this to simulate large networks of microservices on my laptop because actually creating 100,000 machines on AWS to go and test something would be very expensive, and my laptop is relatively cheap because I already have it. Okay, so GoPi, just wrapping up now. This is the nearest I could find to a GoPi. It's a Pi, it's a Raspberry Pi, but I can't find a picture of a Pi next to a gopher. So we've got a Pi Raspberry, Go Raspberry, whatever. So, interesting things here. We want to create a dynamic channel protocol. There's an actor pattern here for Go. I also created a partition service registry and did some logging and tracing. So this is the dynamic channel protocol. The top line shows you a message being sent to a channel. That's what the funny arrow-shaped thing is. And the message is of type GoToCall.message. GoToCall is the package. And this is a GET request. And then there's a listener, the timestamp, a context, and the query, which in this case is just why, because that's a good request to ask people. So the message structure, I did use some promise theory stuff because I felt like using names from promise theory. So the imposition is basically the request type, and the intention is the payload. You can blame Mark Burgess for that. But the second thing here is the response channel, which is a channel of type message. And this whole struct is of type message. So this is like a linked list structure has to contain a reference to the list, right? This is a chained channel structure. So the channel contains a reference to a channel of, the type of the channel contains a reference to the type of the channel, so I can send a channel over a channel. So this is how you make dynamic networks of Go routines, right? Once I've got it set up, I can send you a message, and I can say, hey, this guy's Matt. And I tell you his Twitter handle, and you can now talk to Matt, right? That was a name drop, right? I told you Matt's name, now you can talk to Matt. So everything is working using this name dropping thing, where it's passing messages around and hooking everything up. So it's sort of a routing protocol. This is the messages I came up with, which is sort of a bunch of different things that I ran into I needed. There's gold coins in there because this was pirates, and pirates have got to send each other gold coins, I decided. But the main thing here is a hello message, which tells you who you are. That's how every instance is identical. So, and the only thing the first thing you do is send it its name, and then you send it, you name drop other things to it. You can tell it to chat at different frequencies, so you can tell it how busy it is, how often it's going to chat to people. You can tell it who. Inform is basically telling it to inform somebody else every time it does something, so that's to set up logging. Then there's get request, get response, put, and replicate, which is a bunch of just read and write, sort of CRUD-like stuff. And then there's forget and delete. Forget means like forget whatever, some key value, and delete means delete the key value. So there's a little bit different. Oh, forget means forget how to talk to somebody else. Right? Like if I name drop, I can also tell you to forget. And then the goodbye message is how you make these things go away. So this is the structure of that. Every process, every actor looks like this. They have a start on a listener channel, and there's no other parameters coming in which are specific to this service or this service. You just pass in everything over the listener, and there's a whole bunch of things coming in. In this case, when you get a put, you want to replicate the put so it replicates the data, and that's basically it. And there's also some instrumentation on here, which is using the context and the trace context and stuff. My simulator is capable of implementing Zipkin format trace records as an output, so you can trace what's going on with it. I also built a service registry. So okay, I can name drop things. That's fine for creating networks of pirates. But if I'm trying to create a microservices environment, I want to actually simulate a service registry, a bit like a DNS or in fact, what I called this Eureka because I copied the Netflix Eureka. It really behaves a bit like Eureka in some way. The code here, I'm running out of time, so I won't go through it in much detail. But basically, if you look at this previous one at the bottom, there's a case Eureka ticker. There's a ticker which wakes up every now and again and sends a message. So at certain time intervals, every actor wakes up and talks to the service registry, say, hey, do you know anyone I should know? I'm looking for somebody that knows how to do this thing. And the service registry will send back a bunch of name drops to people, to instances that know how to implement that service type, right? So there's a service type as part of the overall instance name, but you get back all the actual instances, but it's scoped to the zone or the region that you're wanting to do it to. So I have lots and lots of these. But I have to pass in the name because you can't use a service registries have to find out their names without talking to service registries, so the bootstrap problem. All right. So that's basically it. There's a bit of optimization in here because you only want to respond. You keep saying, is anyone new out there? And you just don't respond unless something has changed. So there's a little bit of recording in here to remember that you previously asked that, and nothing's changed since then. So like I was saying, I built a microservice thing, and I'm not going to go through those slides. I went through them at the GopherCon talk, and that video is up somewhere. So I'm just going to wrap up now. So CSP, a little bit too limited. Pi calculus syntax and the proofs are a bit incomprehensible. So I think Occam-Pi, and particularly the paper by Welch, there's an enormous number of interesting examples in there of parallel algorithms written in a very understandable syntax. So it's a good place to go and a great history. Go, the concurrency syntax does work. It just gets clumsy. You end up using weight groups and things, and it's a bit messy, but you can implement everything that's there. It's just kind of clunky to do. I think there's some useful idioms here for building actor-based systems and things like that. And there's these neat tricks like passing channels over channels to kind of get stuff to be more dynamic. Somebody was saying it's a bit like continuations, and if you squint at it, it's sort of a bit like that. And it's been working well. So that's basically it. Some Q&A, and then we're off to the next one. Thank you.
All right, questions?
Thank you very much for that. You mentioned what happened to the mobile types, and do you have any sense of why that was not included in Go?
I don't know why mobile types weren't included in Go. I was sort of, the thing with Go is not to ask for them to change it because you generally don't get a good response. There's a few things in there that most of the things you want are not there for a reason. Like I wanted to be able to test channels to see if they'd closed, and apparently you can't really do that in a safe way, so they decided not to let you do it. There's a bunch of things like that. I do effectively have mobile channels. Now, the system is not as heavily typed as Occam-Pi. Like, if you use your channels incorrectly on Occam-Pi, it can tell because they are truly mobile, and it will give you a syntax error unless you get everything exactly right. And it's one of the most frustrating things I've ever done is to try and get past the compiler with an Occam-Pi program. I mean, it has got so much static checking of the parallel behavior of your program that it's just unreal. It can see things that are really, really deep in your code because it was designed to do that. The language was designed to let you do that. And I don't think Go was designed to have automatic reasoning systems sort of applied to it to say whether you are deadlock free or something like that. So I think it was just, they were designing for a different audience and a different purpose, I think. But you can do mobile channels, sort of, except you can still access them at the other end too, so they aren't really mobile channels, you're just passing things around. Yeah.
Thank you for the talk. Right here.
Oh, there, sorry.
So I had a question about the mobile types as well. Are they different than linear types in a substantial way, or is it just sort of an artifact of
It's
time
about the
that
syntax checking. It's like if you've got a process that's executing and you want to send it somewhere else to run there, you want to be like syntactically sort of, you want to be able to prove that the thing can no longer run here if you're going to run it somewhere else. Otherwise you've done some kind of weird forking of the executing program. Well, I guess it is a fork of the program in that case. So you want to be able to know that you're doing that in some way. Mm-hmm. So it basically, think of Pi calculus. I mean, there are really pages after pages of proofs, which, I mean, if you're a theoretical programming, I don't know what kind of person you have to be to read those proofs, but there are people that can read them and they prove that these things work. But the basic idea of name drop, as I called it, like me telling you how to talk to somebody else, that three-party thing, that's almost the first part in that paper, and it starts there and then it gets complicated. So there are some diagrams showing how that works and how you're passing around references to other things. But like I said, I gave up fairly quickly on that paper. I was giving, come on, show me a page with something I can read on it. Okay.
Any questions on this side?
Over here.
All right.
Nope. Okay. All right. Thank you so much.
Thank you.
Great.
Here's our main talk. This is Paul, and then I'm going to tell you a little bit more about him. So Paul has a new startup called Earth Computing, and you can think of it as solid ground underneath the clouds. That's very poetic, Paul. For fun, Paul likes to skydive out of Russian jets over the North Pole, scuba dive with sharks, and investigate the implications of dark matter and dark energy in the universe. A few of the companies that Paul has worked at: Apple, Replicus, Veritas, Quantum Corporation. Apparently you were a distinguished engineer, director of architecture and performance chief, and chief scientist for IR at Sun Microsystems. Yeah, I learned a lot about you. There's a bunch of things. Okay, so he served as VP of Technical Activities and VP Standards for the IEEE Computer Society. And his passion for dependable computing came from designing systems and software for an experiment which performed extraordinarily well on NASA's space shuttle. So Paul has a PhD in physics from the University College in London, and he's also a graduate of the Stanford Executive Program. Let's give it up for Paul.
Well, thank you, Inez, for that wonderful introduction. I would like to tell you before I start here that I am completely terrified and intimidated by the intellectual horsepower that's in this room. And being able to give this talk at Papers We Love on perhaps one of the most influential papers that's ever been published in computer science is truly an honor. And I feel honored and excited that this particular audience, the Papers We Love audience, who I've grown to respect and to have some affection for over the time that it's been created, and thanks to all of the energy that Elaine and Inez have put into putting this together. So what I'd like to talk to you about today is going to be a bit of a winding tour. I have way more slides than I can possibly get through, so I'm going to go through them very quickly, but I have a plan. And the plan basically is to say, let's talk about what Lamport really did in this paper. It was a magnificent paper. It transformed the way that we think about distributed systems. And I regard this as an unfinished revolution. And that theme will pervade my talk. And at the end of the talk, I would like to begin the conversation about what do we need to do in order to be able to move this revolution further forwards. So one of the main things that happened when distributed computing was being developed was this sudden realization that, yes, we have to think about time differently, we have to think about causality in events, but then, oops, it's failures that cause all the problems. And so we took this big left turn and suddenly had to start looking at other issues, like, for example, failures are very much related to a notion of time, as Leslie Lamport mentioned in his paper. And then we're going to talk about what computer scientists and physicists think about time, because they speak two different languages, and it's interesting to see how they each articulate this problem of time, which everyone thinks they know what it is, but no one seems to be able to describe it in ways that reflect what's going on in our universe and inside our computer systems. And then we're going to have a moment. You've all been primed, right? You saw the digital rain before we started. There is a belief system that pervades all of us, and it's because we're human, about how we think about time. And what I want to do is I want to try and sow some seeds of doubt, and perhaps make you go away and perhaps lose some sleep tonight about what you thought you knew about time. Now, of course, I don't have all the answers, but I do have some damn good questions. And then we're going to talk a little bit about quantum computing. Of course, you all knew that was coming, didn't you? And then the thing that I think is the most interesting right now to unify the disciplines of physics and of computer science is something that I'm going to call reversible computing. And then we're going to have the Vive la Resistance at the very end of this to continue this wonderful revolution that Leslie Lamport started for us. So, Leslie's paper, Time Clocks and the Ordering of Events in a Distributed System, 1978. What was this all about? Lamport clocks. Now here's a nutshell. Lamport clocks are about assigning labels to events, and that those assignments must be causally related. So what do we mean by causality? One thing causes another. We all think we know what causality is, and it's often used in a statistical sense. Physicists tend to use it in a very different sense. In fact, most really good theoretical physicists don't ever use the word causality. That's very interesting, because therein lies the insights into what might really be going on inside how our atomic particles work, inside how our computers work when they're talking to each other. So let's go further into this. Looking into the paper itself, the concepts of one event happening before another is really what a distributed system is, and what Leslie created for us is an understanding of partial ordering. And the first time I read this paper, I had to go to the dictionary. Wikipedia wasn't around at the time, and try to understand what partial ordering was. And I want to distinguish between a partial order and what we'll talk about in a second. This whole issue, though, is that time is really about the ordering of events. And the basic notion of the order of things is a mathematical concept. And what Leslie did for us is he applied his impeccable mathematical skills to simplify and help us understand and reason about this concept of order in a distributed system. Now, what is a distributed system? It's a collection of distinct processes which are spatially separated and which communicate with each other through messages. Now, as soon as things are spatially separated, of course, we all start to think about things like special relativity, which is mentioned very strongly in this paper. But the key concept that was introduced by Leslie was this thing called, it was a relation between two things. It was called a happened before relation. It implies something very significant. It says, this happened and then that happened. And it's an absolute invariant. There is no question about that fact, and you can use that as a premise in your proofs and how to understand and reason about distributed systems. Now, there is something very interesting here. This idea of happened before is something that you'll hear from lots of people who've read this paper. You'll say, yes, Leslie created this thing called happened before. But what most people don't realize but Leslie articulated very well, but most people don't realize, is that happened before is meaningless unless it's intimately associated with happened where. And of course that leads us on to this notion of space-time diagrams, because Leslie was inspired by Minkowski, who generalized the whole notion of space-time that Einstein came up with. And so he created this diagram, which is, you'll notice that this is different to many of the diagrams that we see in computer science. Computer scientists like to draw time on the horizontal axis. Leslie drew this time on the vertical axis, so time is going up in this diagram. You have three processes, process P, Q, and R, and they're sending messages to each other. And the messages have wavy lines to imply that their transit time may not be deterministic, and you may not be able to assume anything about that. And what he then did is said, well, if we try and put some tick marks across these things and say, these things happen in this kind of order in a distributed system, it turns out that the durations really don't matter. The only thing that counts is the ordering of events. And so stretching out those tick marks, you get to understand that there is this causal relationship between one thing happening and another thing happening. Now, I won't insult the intelligence of most of the people in this room. Most of you actually have probably read this paper, at least have heard of it, and you actually do understand because you have to code distributed systems which do these kind of games. But let me try and raise some interesting insights into this paper that perhaps are not so obvious to at least computer science. Of course, these diagrams look familiar. This is called a space-time diagram too, and physicists tend to draw their axis for time in the vertical direction. And Feynman diagrams were a huge breakthrough in simplifying the way that we think about physics in the middle of the last century. So going up on the left and the right-hand side, we've got these electrons. There is a photon, which is the messenger particle, which goes between them. And you can calculate everything you need to know from these Feynman diagrams much more simply than we were able to do before. And this was truly a revolution in physics. But it's written on this background of time. Notice that the paper behind it, the whiteness, is actually time going upwards, time going moving or evolving completely as a single entity behind this sheet of paper. So what I would like to do is I'd like to draw a discussion here between physicists and computer scientists about the notion of time. And we will go backwards and forwards. And what I'd like to do is treat the first third of this session being the description of Lamport's paper. The second third will be what's changed since this paper, because this paper is now 38 years old. So this happened before relation is a single arrow with a single line in the middle. This basically gives us a deterministic orders of events at a particular place. And then there is this thing called a total order, and which I'll get to on the next slide. But you'll notice that all of this is formulated around a notion of special relativity. It's quite natural for the readers of this paper to think in terms of special relativity. And there are some assumptions behind those thoughts of special relativity which still plague physicists today about how the universe really works. So this notion of different choices of clocks which satisfy this clock condition gives us one total order, and there can be many total ordering relations which extends this partial order relation. It's only the partial ordering which is uniquely determined by the system of events. The global order, there can be many of them, many, and we all know this. This is all of the different executions that you can get in your code when you're executing them on a distributed system. So what's going on here? Every message is eventually received. This is an assumption. He also assumes that the process can send messages directly to every other process. In other words, we have an any-to-any addressing system. There's nothing in between. I can send a message directly to something else. What Leslie is really doing in this paper, and not many people get this to begin with, is introducing this notion of state machines, distributed state machines. So you have this notion that we're all familiar with in electrical engineering, computer science, called a state machine. One of those is on every machine. And our job is to send messages between these state machines and to try to get them to behave in a way that we are wanting them to in our systems. Now, I'll notice that the note at the bottom here that those words, the precise algorithm is straightforward, and we will not bother to describe it. It turns out that all of us know that there are some interesting distinctions. Leslie totally viscerally understands his own Paxos algorithm, and there's been a very extended discussion in the community over a couple of decades about whether Paxos is easy or not. I leave that up to your own individual taste, and I actually find it really quite refreshing to read the Paxos algorithm, and I found the Paxos Made Simple paper actually a lot more difficult. Which goes to show that there's something going on here that was deeply understood by Leslie when he did this, and we're just struggling very often as computer scientists to try to articulate how this works, and the best way that we do that is we write some code and we try it out. But sometimes we have to write an awful lot of code. And one of the problems that came out of that early paper is Leslie's acknowledgement that he was trying to operate some of these algorithms in an environment where there was no failures. So this entire concept of failure is only meaningful within a context of physical time. Without physical time, there is no way to distinguish a failed process from one that's just slow. And we all know this result, and it's been generalized in something called the FLP result, the Fisher, Lynch, and Patterson. All of you, I'm sure, are familiar with that. But this is where the genesis of these ideas are in this particular paper. And there are many other shadows of these kind of thinking that Leslie created in many of the great papers that have been published ever since. So this is one of the reasons why this is one of my favorite papers. So let's take a look. Almost everyone I speak to says, oh, this is the paper that Leslie introduces special relativity. He teaches human beings, programmers, a little bit about relativity so that they can understand that their ordering of events in a distributed system can never be deterministic in a distributed, spatially distributed system. But here's the what I call the infamous footnote. After describing special relativity, he then goes on to say in the second part of the paper, which discusses the synchronization of clocks in an environment that doesn't have failure, he discusses that he now takes the Newtonian space-time view, and that if you want to calculate the relative time somewhere else, either through a gravitational well that you're in compared to the other nodes, or the speeds, you can always go back to the equations, and from Minkowski space, in theory, you should be able to calculate the time that someone else has. So if you're on the Earth and you have a twin that shoots off in a rocket to Mars and he's going at some fraction of the speed of light, in theory you'd think you'd be able to look at your clock and calculate what speed he's going at, and then be able to calculate how fast he is aging on that spaceship. Very important concept here, and this is reflected in Leslie's paper. That reflects a continuum. The idea that your time frame is smooth, it's differentiable, and that the time frame of your twin on the spaceship is also differentiable. So therefore, you should be able to map between the two. And the concept in mathematics is called diffeomorphism. I had to look that word up in the dictionary too when I first heard of it, probably about 10 years ago now. So let me summarize. What did Leslie do for us? He basically took us from doing engineering with chewing gum and baling wire and introduced a discipline of mathematical thinking into the way that we should think about distributed systems. And I think he created a huge service to all of us. He revolutionized, in my mind, the way that we engineer our systems in real life, in real companies, and in the real world that we live in. And that echo of his discipline exists throughout all of computer science today. And of course, we're still challenged with this. Sometimes we just want to get things done, we want to get a product out, we just want to try something out. The investors that are supporting you just want you to get a product out to see if there is a market for it, and so on. So we're often torn as engineers and as scientists between how much of one of these and how much of the other do we need to do. And what I would like to introduce to you is the idea of BL, before Lamport, and AL, after Lamport. So, who is going to finish this revolution that was started by Leslie? And the revolution is really all about a general theory of concurrency. We really don't understand time. In fact, I would go as far as to say that both physicists and computer scientists do not understand time. But at least physicists will admit it. So we're looking about this problem of defining what time is and trying to viscerally understand what it means to us, because it's not easy. As human beings, we are evolved into a Middle Earth, into a millimeters and meters size frame, and into a low velocity time frame. We aren't biologically programmed to be able to understand time, so we have to use our brains and the kind of discipline that great scientists and engineers use to get to the essence of the theory of what this really is. And I mean, one definition by, I thought this was Twain's definition before, life is just one damn thing after another, is the happen before principle, I guess, in life. But there was another one by Albert Green Hubbard, American writer and publisher and anarchist and libertarianist and social philosopher in the 18th century, who basically said that life isn't just one damn thing after another. It's the same damn thing over and over and over again. And that gives us a hint as to really what our notions of time that might be that need to be re-examined. So what does Leslie think of time? So this is a picture out of a paper that he wrote 2 years after the one we're talking about here. This notion of a space-time, there's the third dimension's missing, but the fourth dimension here is shown in the vertical axis of time. And so we all understand that there's this horizontal line when the speed of light is in units of 1. And we know that this forward light cone coming from this event E really means that anything that event can influence has to be inside that cone. It is unable to causally influence anything outside the cone. We've all learned this. This is called Minkowski space. And one of the things that's very interesting about Minkowski space is that Einstein didn't like it in the beginning. In fact, he dismissed it entirely and said it's totally the wrong concept. And then after a while, and then he was finally taught how to do tensor calculus, he finally realized that he can use it to formulate what then became general relativity. And so for 100 years, it's actually 101 years now, I think, this year. For 100 years, we've never questioned whether or not Minkowski space was correct. And it turns out that people have been questioning it, but they haven't really been heard. That's beginning to change. It's beginning to be change for some very interesting reasons. So, what are all the different ways that people think about time? So we look at different computer scientists. Mark Shapiro always derives his time on the down axis. Carlos Becerra does his time going to the right. Newton's time, of course, is supposed to be the same everywhere, flowing equitably everywhere. I tried to find some really nice pictures for this, but the best picture I could find actually was this one. And Carlos had found this online, from some touchy-feely California website. But it really expresses something very interesting. It says, what's really going on here on this line, which is going from the infinity in the past to the infinity in the future. And we just happen to be at this moment right now that we call the present moment. This whole idea of an infinitely long line of a continuous nature is actually problematic. It turns out that even if you take the simplest version of this, which is called a real line, which goes from 0 to 1, it's a mess. Mathematically, philosophically, scientifically, it's a mess. So, Carlos, being more of a computer scientist than a physicist, is actually trying to get to the bottom of this. And so the whole idea about what time is here is instead of having cause, effect, cause, effect, cause, effect being this linear order of happen befores and happen after, he basically says it's all mixed up together. You get causes and you get effects and more effects and the more causes. And you really can't see what's going on. And it's a little bit like that. But where do we get the notions of what's going on here in terms of physicists talking to computer scientists about what's going on? And of course, what we've learned is that from what Leslie had done originally, which is a scalar clock that applied to the entire distributed system, unnecessarily restricts concurrency. And so what was invented soon after that was vector clocks. And vector clocks basically are adding a process ID or a processor ID with a scalar and attaching those as payload to all of our messages, and then being able to construct the partial orders or the total orders that we're looking for our behavior of our system. So Carlos is one. I'm going to describe some of these people as either Ptolemists or Copernici. And the reason will become very obvious shortly. Of course, when we get down to the nitty-gritty of this, when we're programming our computers, all roads lead to linearizability. So there's an interesting first concept here, and that is a distinction between what we call the God's eye view, and that's nothing to do with religion. It has to do with what programmers think they can do when they're reaching out across their networks and trying to program a computer or a set of computers in a distributed system. The God's eye view, is omniscient. It can reach out. It can think about things. It can see everything. And then the opposite of that is the local observer view, or the worm's eye view. And this is the point that was basically made about the ordering of events, because only at the local observer view can you actually distinguish the ordering of events. Keep that in mind as we go through the rest of this discussion. So I'll leave it up to you to decide who's a Ptolemist and who's a Copernicus in this next part of the discussion. We've kind of reached the point where we've reviewed Leslie's original paper, and I hope I've not missed out any of the important concepts that were in that. I thoroughly recommend that you go back and read it again. Over the last 20 or 30 years, I think I've read it probably 14 or 15 times. And every single time I come back with a different understanding and a better understanding of computer science. So we do have some friends who we might look upon to say who's providing insight and articulation as to how do we build reliable systems. Because if you remember, we took this left turn away from vector clocks, away from clocks, into how do we solve the reliability problem. And of course, that was magnificently addressed by Leslie Lamport's perhaps second most important paper, which is all about Paxos. And so we have lots of other friends that understand that there's stuff going on here. And so because these are very difficult issues to understand, Jim Gray and Pat Helland had this paper where they really declared that you can't solve this unless you have a master-slave. And then they thought about it for a few more years, and they said, oh, sorry, no, we didn't mean that. Actually, immutability changes everything. And then we found out that we all like that idea because it sounds like we can build robust systems that are robust to different kinds of failures and perturbations. And so that sounded pretty good. And then all of a sudden, he says, just a moment, and this is last man says CMQ, he said, hang on, it's all about Heisenberg. So who else are we talking about here that is thinking along these lines of how do we deal with this problem of failure, which is really the bigger problem in building distributed systems? So Sean Cribbs is very famous for a talk he gave at one of the conferences a couple of years ago, and he's articulating Pat Helland's diagrams here, which says there is a serious problem here when that last operation on the network gets lost. Whether it could be servers talking to each other, or a request response system, or even if you just fire and forget, there's a fundamental issue when that last thing gets lost. And we never know if it gets lost. And this is, of course, very well known. And Jim Gray had a proof for it to say that there is no bounded number of messages that can guarantee that this ever terminates. Now, that's thinking of it, of course, only from a point of view of time that is irreversible. So let's see where this leads. We already know that there's a problem in our computers. You already run NTP or PTP on your systems. You already know that if your networks are down and your computers are not talking to each other, all sorts of strange things happen. So you can see here in this diagram that server A's time reality depends upon the messages it's sending to server B and the messages it's sending to server C. But server B independently and server C all have their independent time reality. There's something going on that when they are not communicating, in other words, there are no causal events going between them or can go between them, then other things are happening that we really don't understand very well. So if you speak to some of the other Copernici in the industry, Peter Bayliss gave a talk here, a very good one, about a year and a half ago. Peter has just received his PhD from UC Berkeley, and as of about 3 months ago, He is now a professor, an assistant professor at Stanford University. So Peter's taking this idea of causality and this interaction of computers to another level. He's basically saying, yeah, if you really want things to be consistent, you have to have them coordinate. But he's also saying, be careful what you're making consistent, because if you don't have to coordinate, then don't. Because every coordination costs you. It costs you the round-trip time of whatever you're communicating with. And the failure events. If that packet gets lost, you then have to recover from it. If you can't talk to it, you get timeouts. And then you get timeout storms, and then your infrastructure starts to misbehave. So who else might be able to help us with some of this conceptual highway that we're on right now, this conceptual jungle of how to deal with this notion of time in computer science? Well, let me just finish up here by saying there's two very good pieces of work that was done about 10 years after Leslie on the vector clocks, and Fidge and Mattern were the two key people who basically independently discovered this notion of vector clocks. But what was more interesting, I thought, was what they did after this, because there's a notion of vector clocks that I think we might want to examine. So you've seen pictures like this before. Notice that the time axis is turned on its side again, and the PQ and R is still there from Leslie's paper, but every computer scientist that I have talked to, other than Leslie, does the time on the right-hand side. There's no reason for that. It's interesting that we can then describe these green and red areas about where this event is in our Minkowski cone that is able to be influenced by things from the past and at the same time be able to influence things in the future. And we kind of understand this, but what if we were to do this and take all of that noise and baggage away and say, oh, we've got some arrowheads on these black lines here. What if we were to turn some of those interactions into reversible interactions? In other words, the blue lines that you can see here, there were originally unidirectional arrows in the previous diagram. They are now reversible. Now, let's see where this leads. Justin Sheehy is now at VMware. He used to be the CTO for Basho, and he wrote a wonderful article in ACM Now that was called "There Is No Now." The myth of simultaneity in computer science. And of course, there was a very famous person who actually agreed with him very much on that topic. And so this question about does simultaneity exist or not? It's like we're very schizophrenic as engineers. We sometimes let it into our thinking and our styles of description. And then we also know, and fundamentally in some other way, that no, there can't be any simultaneity. And in fact, that's the heart of the principle that we're going to try and examine here a little bit. So simultaneity is a myth. And the reason is because simultaneity means that I know what time is for you, whether you're whatever depth of the gravitational well that you're in, whatever speed that you're moving at, whatever distance you're currently at from me. In theory, if I can understand simultaneity, I can calculate what time should be for you. This is wrong. This is a fundamental physics principle that even the physicists argue about a lot, but it's pretty much been proven conclusively that Einstein was right. Simultaneity is a myth. And the reason is, in order to determine the simultaneity of distant events, you have to know the velocity. And to measure the velocity, you have a knowledge of the simultaneity of distant events. In other words, there's a circular argument here which leads to a really interesting concept, and that is that you can't ever measure the speed of light, the one-way speed of light. The way we measure interactions and the way we measure the speed of light is always with a two-way interaction. Look this up on the web. It's called Einstein synchronization. Fundamentally, in our physics, in our mathematics, and everything that we measure, we are unable to measure the one-way speed of light. Now, why is that? Well, it's because you've got your time clock going on inside your environment, and I've got my time clock going on, and we think that clock is ticking away against this background of time. This background of time is what fools us into thinking that I can measure this time and therefore I can measure the distances out, and if I know it's the speed of light, then I can calculate exactly how far away they are and so on. Well, it's a little bit more complex than that, and we'll go down the rabbit hole in a few more slides. So let's go back to reliability. Reliability is absolutely fundamental to distributed systems. But it's also, because this last write, when it gets lost, loses the causality of the thing that can affect your algorithm that affects the behavior of your systems. So we all know that Kyle is very fond of being very direct in the way that he describes things. And he wrote this wonderful paper, not paper, it was an article in ACMQ with Peter Bayliss, in fact, about the network is reliable. And it turns out that these failure modes, drop delayed, duplicated, reorder packets, are right at the heart of all of the problems that we have to deal with making distributed systems reliable. Many of you have already experienced this. You're probably experiencing it on a daily basis. I have seen situations where a switch starts to misbehave for a few seconds, which causes the application to misbehave for a few minutes, which causes the database to be out for 2 hours. And in large infrastructures, most of you have experienced this. In fact, the larger the infrastructure, the more often it happens. So the cascade failures that cause these unexpected outages of large organizations, some of the most brilliant, best engineers in the world that work in some of these large organizations, they experience this. And you see them in public when their systems are down. So what's at the heart of this? My guess, and I would assert to you, is that we still don't have a good theoretical understanding of this relationship between concurrency and failure tolerance. Now, we are all trained as engineers, we've had lots of education on this, but there's something more fundamental going on here. So let's take a summary of what Leslie did for us. He defined it happened before relation, which is a partial order. He defined logical timestamps, which form this arbitrary total order. And this concurrency efficiency loss that you get from a single scalar gets worse when you add more nodes to the distributed system, when those nodes become more spatially separated. When our networks and processors get faster, we notice the slowdown a lot more, and our processors are comprised of more cores. And so we should be highly motivated to dig into this theory, to continue the revolution that Leslie created from this original paper into where are we going now to finish this revolution that started. So one of the things that came out was very interesting. The size of these vector clocks becomes a problem. We all know that a single scalar moving around, has to be an integer of some kind, and we make believe that we can send one of those around if it's large enough. You have a send around a 64-bit integer, it's going to be many, tens of years perhaps before that integer is going to overflow at some clock tick rate or whatever else that you're using for this logical clock. It actually gets worse when you use vector clocks, because now you have this explosion of all of these different processes which you have to hang on to, which become baggage on all your messages and so on. And so there's lots of work been done to try and mitigate this problem of the explosion of the size of the messages with processes and this issue of the clocks. Everyone thinks that, well, if you just make the integer big enough, it's longer than the lifetime of the computer. It's going to be replaced in 3 years anyway. But what happens when you get errors? What happens when all of a sudden some kind of corruption or bit flipping by cosmic rays going on in your system puts your integer suddenly close to the point where it rolls over? We have seen entire infrastructures grind to a halt when that kind of error happens. So there's something we haven't yet solved, a problem we've swept under the rug about this notion of things incrementing monotonically, indefinitely. So let's take a step back. Let's just say, where have we seen this before? And I want to give you an idea about, we're not talking about something complex here, we're talking about an intellectual vantage point. And we knew centuries ago that when we were looking at the sky, we thought we were the center of the universe. The Earth was the center. And we would see the sky, the stars, and the sun go around us constantly. And we would find that some of these stars were wandering around a planet. This is Latin for a wandering star. And we had to have a theory. And the theory was, let's have some circles, the big ones, and then some smaller ones, and then some smaller ones. And when you add them all together, you get an extremely accurate prediction of where these planets are going to be next or the next night. And this this coincided extremely closely to the measurements that were being done by Tycho at the time. And so there you go, beautiful theory, epicycles, and it matched the measurements that we were making. And then along came Copernicus. So the intellectual vantage point changed from the Earth being the center to the sun being the center. And all of a sudden, instead of having these crazy patterns that were happening in the sky, we suddenly understood everything initially as circular orbits and then as ellipses. And so it's suddenly, all of a sudden, our scientific world, our astronomical world became a lot easier to understand. I would suggest to you that we're on a precipice of that exact kind of thing happening right now on our understanding of time. And what I would like to do is to encourage computer scientists and engineers and physicists to have a conversation about this, because I think we're very close. So let's see if we can begin this conversation. So I'm glad that Adrian talked about the life of pi, or the life of Occam-Pi in his talk. And it turns out that pi is a very popular concept and number in physics. It appears everywhere in all our equations. And so we think there's something very magical about pi going on here. And so, for example, when we try to understand how many, what this thing is as a rational number, and then we try to put it into our equations, and we get this incredibly simple equation that ties together ei, pi, and 1 and 0, which is like all of the interesting numbers in number theory, into one single equation. We say, oh, something very interesting must be going on there. And in fact, physicists use this all the time to be able to simplify what it is that they're doing. So instead of the life of Occam-Pi, let's follow the life of Pi Patel as he goes through his experience. You'll notice that there's a frame of reference that he's standing on here. That it's actually the water. He's looking at this smooth background of water, and that's the world that he lives in. But it's real. He can touch it. He can swim in it. He can drink it. Maybe not drink it, but he can interact with this background, this smooth manifold, if you like, of fluid. And this thing sometimes can be so incredibly fluid, so incredibly flat, that it looks just like a mirror. It's just like we think that that's what time is, and only when we start messing around with going faster and faster do we see that this thing kind of distorts a little bit. Or maybe even when we have these black holes that spin together and cause a chirp, and now LIGO, the experiment, can measure these small perturbations in gravitational waves. So we have this view, this concept in our minds about this background being very, very smooth. But it's not really like that. When we start to see the waves chopping up and falling apart and drops of water completely disconnected from the rest of the water in a storm, then we get to realize that our concept, needs to be changed. And this is, of course, the conjunction between general relativity, which is all about smooth manifolds, and quantum mechanics, which is all about discrete measurements. In fact, we know with some great certainty that everything in time that we know of real time is discrete. We only measure discrete things in quantum mechanics. So we can take Peter Parker and we can say, well, what are you made of? Is this idea of a manifold, a mesh, a set of tick marks on our background of time? Is this something that we can look at in a different kind of way and come to some conclusions about what a new theoretical basis might be for time? Because that might give us a new theoretical basis for concurrency. So what is time? Well, first of all, I'm going to introduce a couple of things in this talk. All time is a tree. You just have to pick your root. Most people think that if there's a background of time, then of course you can go to any atomic clock and ask it what time it is, and it will tell you. Not. It turns out that the international time is actually an average of all the atomic clocks in the world, and they adjust relative to each other. There is no background that any one of them has any particular claim to. Secondly, what we're starting to realize now in physics is that entanglement is the root of time, and that anything that can happen can unhappen, because in entanglement and in all quantum processes, things go forwards and backwards. Now, we know how to make things go backwards in computer science. What we do is we have a transaction manager, and we ask one computer, are you ready to increment your bank account by $1 million? And are you ready to decrement your bank account by $1 million, and then they do a commit, and if any of them don't give an acknowledgement, that last acknowledgement that keeps getting lost, then you do a rollback. That rollback, if you like, in computing is a crude form of reversible computing. So we're all familiar with the concept, we just haven't put the pieces together yet. And then finally, most importantly, any message that can be sent can be unsent. So let's follow us down this rabbit hole here and see what the physicists have to say. So only recently, Lenny Susskind at Stanford has started to realize, after a conversation with Juan Maldacena about, this is the famous person who discovered the holographic principle, that ER equals EPR. Now, of course, if any of you are physicists, you will recognize that EPR is Einstein, Podolsky, and Rosen, which is what entanglement is. Some of you are familiar with general relativity and tensor calculus. You'll recognize that ER is Einstein, Rosen. So all of us will recognize this as Star Trek, right? The wormholes through space, the faster than light travel that we all are very fond of in our science fiction stories. So it turns out there's a discovery, even though these seem to appear to be very different things at very different scales, that they are exactly the same thing. They're identical. Really interesting insight, and this is only very recent. So, what would Leslie say about that? Of course, this is very important because Leslie is a disciplined thinker. And what we need are disciplined thinkers, or at least to be able to give the disciplined thinkers the time and the space and the encouragement to do this work for us, because only then do we think we can actually move the ball forward on this agenda for a new general theory of concurrency. So, who would be able to prove it for him? Well, it turns out that this gentleman, John Bell, is at the heart of the whole entanglement discussion. John Bell had this amazing book called The Speakable and the Unspeakable in Physics. And the reason was, physicists argued indefinitely about this problem for many, many years, almost a century. It was so bad that there was a saying for it. It was like anyone who talked about this problem or what's going on under the quantum hood was like a philosopher, and don't talk to them. And you would be disenfranchised from the physics community for even asking questions of what's really going on down there under the hood. And it's only now, literally in the last few years, are we starting to realize that some of the most interesting things ever is going on down there, and the real physicists are starting to look at it. This problem used to be called shut up and calculate. And John Bell settled the question. He basically proved mathematically that you could distinguish between Bohr's view of the world and Einstein's view of the world. And many people would say that Einstein lost that argument. And then more recently, we're starting to realize that no, it's a much more subtle argument than we ever expected it to be. So what is entanglement? We have got two particles. The source in the middle typically is some kind of down converter where you give it a single photon and it spits out two photons on either side of half of the energy to either side. So these photons, in a way, are related to each other. They were given birth at the same moment. They're entangled in a physics sense. And what's interesting is if we try to measure the result on either side here, we just get a random answer. It's completely random. But what the most amazing thing is, and it's really hard to wrap your head around this, but I would encourage you to get online, go and watch some of the amazing videos that are online right now, particularly from the Perimeter Institute and from Caltech. What happens is when you measure one of them, you're effectively stealing information out of it so that they no longer remain entangled. But when you measure it, this collapse of the wave function, as what it used to be called, when you measure it, one side might be measured as spin up, and when you measure that, you know exactly what the other side is going to measure. You say, well, what's the big deal? The big deal is this could be a meter, a kilometer, it could be a million light years apart, and you still, and I use the word very cautiously, instantaneously know what the other is able to read. Now, of course, it has to send you have to do a particular measurement. It's called preparing the measurement. So you have to ask a question. Which way are you spinning? And when you get the answer, you know that the other side that was entangled was exactly the complement of that. So that's the fascinating thing about entanglement. But it gives us at least a hook to be able to start thinking about, well, what should time mean for us in computer science? We should stop listening to our clocks and our computers, giving us this false illusion that this is a smooth manifold, and perhaps say that maybe Leslie was right all those years ago. It really is all about the events, it's about the interactions, and it's the causality that counts. So Einstein was very prolific on his discussions about space-time. And one of the things that we realized from his very original paper was that his whole reasoning was about a clock. It was about a photon clock. So if I've got a clock, a photon going backwards and forwards between two mirrors, he deduced all of special relativity and then used that as a basis for general relativity 10 years later. That was all based on Minkowski space. And Minkowski space is what Leslie Lamport used as an intuition, used as a ground for building his understanding of distributed systems on. And what we're starting to realize now is a lot of physicists are saying maybe we should start to question Minkowski space, because Minkowski space is kind of like a smoothly bent Newtonian time. In other words, there's a background at which we think things are causing everything to change in kind of together in concert. And that's exactly what it appears not to be happening in entanglement. So this is Joe Polchinski from Caltech. We know that quantum mechanics breaks down, and so therefore our understanding of space-time must be wrong. And then, of course, we have the computer scientists and say, well, it doesn't matter. What we can do is we can create these data structures called semi-lattices, which will allow us to be able to have no interactions between things for a while. And then when we bring them together, we have a basis, a state basis or an operational basis in order to be able to merge them, these data structures. So this is a solution partially to the fact that you are overwriting something and that you don't want to lose any information. You're basically keeping as much information as you need to merge them back again later. So the edge of our knowledge right now is on these things called CRDTs, or conflict-free replicated data types. And we have Lindsay Cooper is the picture, by the way. That's not Rasputin, I just noticed. But you guess what, Rasputin's coming. And so we also have, some other incredibly good minds in the physics department. So Mark van Romsdonk gave a fantastic essay about 5 years ago about this notion of, well, maybe, just maybe, time emerges from entanglement. In other words, we now know that there's something fundamentally wrong with space-time, at least the way that we've been conceiving it. What else might be a possibility? And his statement is that space-time is built from entanglement. This has gone from being hugely controversial to starting to become almost, and I would probably predict that within the next 5 to 10 years, this will become standard physics and it will be taught in all the schools. So, who else might be able to give us a view of the computer science notions of what's going on? And Chris Micklejohn, of course, is working very hard on his PhD in Europe right now, trying to think through some of these problems. He's come up with, I've seen some marvelous talks from Chris, and he's clearly trying to impersonate Einstein here with his haircut. So who else is going on here? There's an Italian physicist who is extraordinarily brilliant. Lorenzo Marconi has done some work with Seth Lloyd. Literally has done not only the theory to say that time emerges from entanglement, he actually did the experimental illustration. And what's interesting, we're starting to find out right now what's going on. There's a notion that when you look at things from a God's eye view, everything seems to look static. In other words, it looks like a wave function that's fixed in this block of thing that we call space-time. But when we look from the inside, from the local observer view, we can see the evolution of what's changing. So this whole idea comes down to a subsystem of an entangled state works like a clock of another subsystem. In other words, you can use one thing that's counting time to measure intervals or events, if you like, in something else that's evolving. This is starting to get interesting. So Max Tegmark is also very much on the leading edge of encouraging people to think about this. He's one of the directors of the Foundational Questions Institute, which every year invites young physicists and people with crazy ideas to write essays, and it gives out prizes to those who come up with the craziest ideas. I happened to be one of those about 2 years ago. But what he also says is that what we've learned is that we really don't understand time. We really don't. It's a new frontier. It's this Ptolemaic frontier of like, how do we change our vantage point from this not so simple position of epicycles to this much simpler position of orbits around the sun instead of around the Earth. So there are some interesting things going on. There are many, many computer scientists and engineers that don't get it right. And it's not an indictment, it's actually just the way we've been trained, the way we've been educated. The world that we live in is telling us that epicycles, work fine, don't question them. And a good example is Maurice Herlihy and Neil Shavat, who are very famous computer scientists and educators, people who I have an immense respect for. And yet in their book in 2008 on the art of microprocessor programming, they actually said this. They defined Newton's definition of time being absolute true and mathematical of itself and from its own nature, flows equitably without any relation to anything external. And their comment on that is that they endorse that view of time. And this is curious because that actual notion of time was proven incorrect over 100 years ago. But the reason that they felt logically entitled to be able to make the statement is because of this belief in a diffeomorphic connection between the space-time that one entity has and the set of messages in the space-time that another entity has, and they both have a common background. So this idea that we all have a common background is what's up for challenge right now. One of the people who's done most of the interesting work on this, he wrote a book saying there is no time. I think this book is now about 6 or 7 or maybe 8 years old. It's Julian Barber in England. He's working at Oxford University. And what he realized is that something very fundamental that he got from Ernst Mach, and then I dug into the history and I discovered that Ernst Mach actually got this from Aristotle. And Aristotle's definition of time, even with all our science and all our mathematics and all our engineering today, we haven't been able to beat. Aristotle's definition of time is change that you can count. So keep that in mind, because this discussion has been going on for quite a while. This used to be called the waves and particles, conflict, and it went all the way back to Einstein and Bohr about them arguing about this. And even Richard Feynman and Schwinger had this long-standing discussion about whether it's waves or whether it's particles, and they jointly won the Nobel Prize on this topic. So Richard Feynman is very famous because of the brilliance that he had in bringing some insight into physics in the last century. But he also had some interesting ideas that suddenly caused him to stop and think, well, maybe there's something wrong with the way that I'm looking at this. And that what we have realized is that he wrote all of the equations of quantum electrodynamics on this background of Minkowski space, this background of time that we're talking about here, that we're starting to see if this is different to, Pi Patel's ocean and this idea of a smooth thing that's connecting lots of things. Maybe there isn't any ocean there. Maybe it's just a void. And this is not a new idea. That many people think of this. I have some speculations on how this works. I would not go into this deeply because this is not the place to do this here. But one of the things that we might find is that I hope that I convince you at least a bit here that there's maybe some question about the way that we're looking at time. And I have gained an insight into how information is shared in a quantum system. And essentially what's going on is time is going backwards and forwards as information is passed from one to the other in a form initially of photons, for example. This all ties in. It turns out that even if it's wrong, it turns out to predict some very interesting things that you might want to do in an engineering sense, and it certainly predicts an interesting way of designing protocols on networks that don't exactly have to be quantum entanglement. They can just emulate them in order to be able to gain some of the benefits. So there is another interesting myth, and you'll read this. Another example, I want to show that this is a common misbelief across our entire industry. So there is there's a book that's called Distributed Systems for Fun and Profit, and in there it basically talks about what you can do if you could make your clocks accurate enough. And what I want to do is I want to sensitize you to the questions you should be asking yourself, or even the person that you're speaking to, when someone talks about synchronizing clocks, and the whole idea that you can make them accurate enough to be perfect. There is no perfect clock in theory. So therefore, they're going to be problematic in practice. And we have to unpick our assumptions very carefully to try to understand what we can come up with differently. So what would we want to do? A general theory of concurrency. Physicists and computer scientists are talking past each other right now. They're talking different languages when they talk about time. If we could resolve this, we might be able to make progress on Leslie Lamport's goal of a general theory of concurrency. And that would be my hope that will happen in my lifetime. So what is this notion about reversible time? Distributed systems today use timestamps, as we know. Interesting question. When I ask someone about, well, why don't Lamport timestamps go backwards? And people scratch their head and look at me very funny, as you can imagine. But why shouldn't they go backwards? Let's imagine you've got a conversation going on between two computers in a field of 10,000 computers, and they happen to know on either side of one link that something went wrong. I don't have enough buffer space, I crashed, or my process crashed, or something went wrong. Maybe locally we can make the logical timestamps go backwards, just to fix these smaller failures that we get, instead of just dropping packets and doing a retry, and then having these retry storms that happen in our data centers. So this idea that all of our nodes can have this common view of time, we know is wrong. We know it's wrong if you just do the measurements. If you're using NTP, you'll know that it's plagued with lots and lots of difficulties. And even though there's been some heroic efforts to improve the algorithms from the original Marzullo algorithm that's used in NTP, you'll know that there's an interesting assumption in the algorithm and in the paper, and that is that there is a assumption of a continuous clock drift, which is smoothly moving from where you think it was last time you talked to it and where it might be now. And the whole game is to try to predict where that clock might be, and then to subtract out the delays on the network and be able to predict, what the time should be. Well, there's been some very interesting results that really point to an interesting flaw that we need to examine, perhaps in the whole idea of how to do things this way. And that is that when a clock is too far away, we say that must be a bad clock and we throw it away. Now, do you know any other scientific discipline that throws data away? The experiment that we're carrying out, by the way, with NTP is there a background of time? And what we're finding is all of these clocks that appear to be bad that keep drifting out of range because we think they're, not made by a good manufacturer, or they are not temperature compensated, or whatever engineering reason we come up with about why that clock is drifting more than we expect. It turns out the issue isn't so much that the clocks are drifting, the issue is that the failures keep causing us to miss what our understanding of time is. So my ability to be able to predict from one computer to another what time I think it is for you is entirely dependent upon how much load there is on the network. And indeed, on how much load there is inside this computer, and how much my caches are misbehaving in terms of the determinism I can expect from making these measurements. So there's lots and lots of issues here that are ready for and ripe for examination. So there is a potential insight. The potential insight is that reversibility can be included in our theory of concurrency. We're not going to be able to reverse a 10,000 computer system and say, okay, switch back to some earlier time. We kind of do that these days. We think we can create snapshots, and then when a failure happens, we say, okay, let's go back to the last good snapshot. Well, there was an excellent paper in the IEEE Explorer magazine just recently about HPC computers and about how the mean time to failure of these machines is going down, and how the time it takes to just record the snapshots going up. And there's a crossover that basically says you can't win when you get past this point. So maybe we need to think about our failures and our concurrency on a much finer level, and be able to stitch up our failures without stopping the system, without doing snapshots on a large scale, but just between these, now I won't call them entangled entities, but let me call them related entities that are talking to each other on a network. Because, for example, Google Spanner tried this. Google tried valiantly to create a simultaneity plane around the planet. It was a brilliant idea, and true time gives us a bracket before which a transaction's happened, another bracket that says after which it's not happened, and after which it has happened. And the window was supposed to go down to something like 6 milliseconds. But even in the paper, you can find all the clues that there's something missing in the theory of what this is based on. And they actually use Marzullo's algorithm, which is used in NTP, in order to be able to try to synchronize time across all of their machines. So it's a really insightful idea to do something like true time. But it belies the underlying assumption that we all have that we're not examining in, that there is this idea that we can make things simultaneous around something as large as the Earth. So there's lots of things. My prediction is this is the year. The papers that might win the Nobel Prize on this topic have probably already been written, and they're on the way to the journals in the physics community. The people who are working on the reversible computation side of this in the computer science community, they're working furiously on this. I just came back from Bologna literally 3 days ago from this conference. And we found some very interesting things. And I've got the slide in here later on, but Samson Abramsky, who's a professor of computer science at Oxford University, basically has taken the tools of computer science, the kinds of tools that Leslie uses to prove his theories in computer science, and he applied them to physics and settled a long-standing problem that has existed about something called Maxwell's demon and the fact that it needs memory in order to be able to do this. Fascinating interdisciplinary cooperation going on right now in order to be able to get to a deeper underlying theory about what time is and about how this physical interactions work. Now, this stuff is not new. The idea that you can send a message and then unsend a message was actually described by Robin Hanson in 1992. And he described something that isn't quite right, but at least it wasn't then, but it is perhaps more right now, especially when we start talking about these new data structures. A computer's task is basically to start at some point and be grinding along for a while and then spit out some kind of result. And what he realizes, remarkably, all these tasks can be done reversibly. So there is the edge right now of thinking, and what I would commend to you to be worth looking at. So what am I talking about here? Let's get concrete. Let's imagine I've got a bunch of clocks. How can you make these clocks reversible? Well, here's the good news. You can make them reversible, and you can get closer and closer and closer to what's really going on under the quantum hood, even if you're emulating things. But the bad news is you can't go back in time and kill your grandfather. It turns out that that idea really only exists when you're in a general relativity, smooth continuum environment, and you can use a wormhole. It turns out the only time that time can go backwards is very, very locally. But it's not small. You don't go backwards just inside atoms. You can go backwards across any arbitrary distance, as we have discovered with entanglement. So what's going on here? If I've got a bunch of computers that are trying to do something, and then all of a sudden, they turn the clock around and they start counting things. Remember what I said about what time is. Time is change that you can count. So at the end of some process, we pick a time, we say, okay, it starts now, and then some arbitrary, observation point in the future as a human being, we say, okay, and let's ask it now what result it's come up with. So we don't know when these things have reversed and they've corrected or fixed some of the bugs and some of the problems that we've had. We don't know how often it went forwards and backwards. All we're interested in is an overall result that's extremely robust, that is robust to any kind of perturbation. So I would like to suggest to you that we start thinking about this notion of reversibility. And the reason why it's interesting is because we think of time as plus and minus. We think of like the future and the past, and we put these labels of plus and minus on it. It turns out that when you reverse time, in even classical equations of Newton's equations, the equations still make incredible sense. When you have billiard balls hitting each other, if you take a movie of what's going on, you can't tell whether that movie is going forwards or backwards. There's something very, very, very important in what's going on there. So why can we do this thing, turn these things upside down? It's called the Born interpretation. And what it is in quantum mechanics is the idea that you take the wave function, you take its absolute value, and you square it. And when you do that, all the minus signs disappear. You get right back to Aristotle's time is change that you can count. I would recommend to you that this is an interesting avenue of investigation, and it could open up new sets of pathways to take us to this revolution that Leslie Lamport started on the nature of concurrency. So the Born interpretation is actually this thing down here. The probability that the wave function is between these absolute signs and then the squared sign here. This is, all physicists use this all the time. This is that thing. When you measure it in the lab, it's a probability in the equations, but it gives you a probability distribution that when you go in the lab, you get exactly that. It's incredibly accurate. This is way more accurate than Tycho's epicycles. It literally gives you exactly the result. There's no, in fact, the entire standard model and what CERN does every single day is based on that thing that's known as the Born interpretation. Nima Akani-Hamed is one of the most famous physicists right now at Princeton. He's at the Institute of Advanced Study, which is the place where Einstein was at. He's a major advisor to CERN on how the standard model works and how to seek new notions of what's beyond the standard model. And he has a series of lectures online. You can watch them. He has quite a few of them. And most of them he begins with a statement that space-time is doomed. Now, of course, there are many computer scientists who are trying to think deeply, many practitioners who are trying to think deeply about really what's going on inside computers. Now, they do have some help. and there's... And of course, it's really saying what Leslie said all those years ago. You know, you really do need to use formal methods for this because you can't think about things in a disciplined way without using the tools of mathematics as the discipline. And so there's some, I would commend you to go online and look at Katie's talks about this. You'll find that there's talks by lots and lots of really bright physicists out there. Entanglement, you know, might explain the arrow of time. This is Seth Lloyd at MIT. Basically, one of the prominent people in the physics community right now who believes that the whole universe is quantum mechanical, and that we're living in this quantum computer, as a few people are starting to call it. And then, of course, Leslie would say, "Where's the proof?" What I'm trying to point out here is that this dialogue, this interplay between computer scientists who have these incredibly good formal tools and the physicists who are often shooting in the dark and inventing things like perturbation theory and so on, really need help. The mathematicians and the physicists traditionally have been enormously fruitful in collaborating on investigating some of the big problems, you know, of our time. And I'm suggesting that it's time that computer science came of age and joined in this conversation and participated in this discussion of what's going on. So who would be able to have a conversation with Leslie Lamport? Maybe Scott Aronson would be able to. Scott's very famous for his opposition to the D-Wave machine and for the conversations with Google. Here's what's going on. If you're trying to measure the duration of something, like on a conventional computer or on a quantum computer, we really have some serious questions if there is no common background of time. It really says, well, what does this duration mean? Well, what it means is that all you can do is count things. It's Aristotle's definition of time. And then you have to seriously ask, well, what is it we're counting? And then you have to ask, well, how deep does this rabbit hole go? This notion of asynchrony that we think we understand in computer science and that we attach these, you know, delays to, which are supposed to be speed of light delays as we think about this thing, well, it may not be correct. It may be that there's a much more concurrency under the hood here than we ever thought of. And if we think about it from a computer science perspective, we may be able to come, you know, hands to hand with a physicist who are trying to, you know, undo this puzzle right now as well. So, one of the things that Scott Aronson does is he points out something very important. Probability is at the heart of all this. And probability is nothing more than predicting something. And you really can't have a probability until you've measured it many times. I know that your venture capital supporters would say they'd like to try and measure, you know, calculate risk or whatever else. That's nothing more than their opinion about what they think the risk is based on their imagination. What's really going on here is that if you really want to know the probability of something, you have to measure it many times, and then you get a distribution, and that's what's accurate. But here's the interesting notion about probability. It goes from 0 to 1, right? I mean, something that's certain is a 1, and something that's absolutely guaranteed to fail is a 0. In quantum mechanics and in reversible computing, probability can be negative. In fact, it goes better. Probability can be complex. So I would suggest to you, take a look at what's emerging right now. You're in the middle of a revolution in physics, in computer science, that is at least as big as what Einstein created 100 years ago and what Leslie Lamport created 38 years ago. You are living in probably one of the most exciting times for this particular subject that I think we've ever seen. So, there are some controversies. Not everyone thinks that this background of time is a problem. They think that it's actually the rabbit hole goes even much deeper. In fact, Lee Smolin, who's the founder of the Perimeter Institute, and he's actually a friend of mine and on my technical advisory board, and he rips me to pieces every time I talk to him about this because he's much smarter than I am. But he basically says that not only is there a problem about the way we're thinking about time, that the laws of physics themselves evolve. And they evolve just like evolution in our biology. They evolve as a complex adaptive system, as things evolve to fit their environment. So the universe itself is an interesting problem. So I put this later on in the presentation that I had before because I wanted to make sure that I got some of the main points over. But I did promise you a blue pill, red pill moment, and I'd like to ask how many people here have read Leslie's paper. First of all, that was on the website. Good. That seems like 2/3 of you. How many people here actually looked at the video links on the website that went to the physics of causality, and there were 2 separate videos there. They were small ones. Okay, there's a half a dozen, maybe a dozen people that did that. So what we're looking at here is when we unstick ourselves from this notion that there is a background of time, or maybe we should question whether there is a background of time, because we don't know for certain yet, of course, whether there is or not, then we might say, well, what are the questions we have to ask? What are the new ways we can think about building our computers? And so what I could do is, I'm running out of time right now, so maybe I shouldn't do this. Maybe I should, we can all go back and get some wine, I think. Do you want it? All right. So this is a Nature magazine, and there's one like it very much in the Quantum magazine, description about this entanglement connection. And so what's going on here is the mathematicians came up with this thing called anti-de-Sitter space, which is kind of like an Escher drawing about how things are related in the universe to a boundary out there. And then what we've discovered is that all of the mathematics is entirely consistent with what we call a tensor network underneath. Well, you might say, well, you're a physicist, you talk about tensors. Well, guess what? Google announced TensorFlow recently. How many of you went and looked up the definition of what a tensor was when Google announced that? Eh? Well, it's a multi-dimensional array with an arbitrary rank, and it also has certain mathematical properties that are distinct when you use that kind of mathematics. So it's not tough at all. It's the same kind of stuff you've done before, so don't be frightened of any of this stuff. Go out there and investigate yourself. So if you keep on going down the rabbit hole here, you start to realize that this notion of entanglement here, basically it means that you have to understand this distinction between the God's eye view of looking at the system as a whole and the local observer view looking at both sides from either way. And then you can get things disentangled. When things start to break apart, you end up finding that they get elongated into this thing that looks like an Einstein-Rosen bridge of a set of particles, and then all of a sudden you find they break off and they snap off into different pieces of space-time. You might say, well, okay, well, there's 2 universes. Maybe that's what happened. You can't talk about 15 billion years ago anymore, because the question about what 15 billion years means is even now up for grabs. What happens, though, is this can happen with 2 computers. When you disconnect the cables and they can no longer talk to each other on the network, there is no causality going from one side to the other. So guess what? You can't predict what the other one thinks the time is. And it gets worse when you put virtual machines in the way. Containers are not quite so bad, but virtual machines especially are, because you can stop a virtual machine on a cycle. It has no idea it's been stopped. And you can start it a second later, or you can start it a minute later, or you can start it a year later, and it wakes up and the only clue it's got is that its notion of time that it has is different to what the network is currently telling it. And notice I said the network is currently telling it, which means it has to be causally entangled with the network again in order to be able to find out what the consensus is out there about what time is when it wakes up again. So these are really interesting concepts that don't have to be, you don't have to have a PhD in physics to think about it. And they do affect what we need to do in computer science as we're going forwards. And I would suggest to you that there's some very interesting things going on here, especially with Maxwell's demon now being proven by computer scientists. We're not just waiting for the physicists to hand down their genius knowledge to us in a packaged form that we can use to design our computers. I am saying that the computer science community, you, all of you, can participate in this conversation and can cooperate in this question of, from first principles, what's going on here, what can we come up with, and can we measure it? I'll give you an idea of something that you might go out and do. Remember I said you can't measure the one-way speed of light? Well, there is this nice little program on the network you can download onto your Linux system. It's called One-Way Ping. So go and try it. I mean, some of you may have tried it. In fact, if you try it between here and Europe, you'll find that many times the packets have been received before they've been sent. So this idea that you can have this notion of time on both sides and try to measure the speed of even a ping, because a packet is a piece of causality that's going from one computer to another. So, what are the takeaways here? Simultaneity is a myth. It's like asking the words at the same time. When people talk about photons going through a two-slit experiment, it makes about as much sense as saying what's north of the North Pole. Negative probability is just as real as positive probability. It's just with the before and the after substituted. In quantum mechanics, all probabilities are complex. All time is a tree. You just have to be careful which route you pick. So who will finish this revolution that Leslie Lamport started? And I would suggest that all of you should participate in this revolution, or completing this revolution that Leslie started. So let me just finish on this topic right now. I am experimenting right now with some of these concepts with some people that I know that will prove me wrong very quickly. And some of these ideas have turned out to be quite robust. I would like to suggest, Leslie was right in the first place. It's not about time. It's about events. And when he introduced happened before, he began this revolution that we're in right now. What I would like to introduce is a notion of unhappened before. In other words, if something goes wrong in a chain of events on one of the steps in a distributed system, maybe I can make that unhappen and then make it go happen again. And unhappen, unhappen again, and unhappen, unhappen again. In fact, you can have that happen, unhappen, happen an arbitrary number of times. But the only thing that you will see further down the chain when you try to listen to it or measure what came to you is the thing that came to you with the correct safety properties of the algorithm or the behavior of the program that you were expecting. The word instantaneous has no meaning in this context. Simultaneously is a myth. I've already said that. I didn't read my slide too much. So let me leave you with another interesting notion. While a background of time might be promiscuous in everything, everyone is interacting with everyone else, entanglement is monogamous. There's only two parties in an entanglement. Think about that very carefully when you design your protocols. So questions. I'd like to do the following. This is a different situation now than you're probably used to at the Papers We Love sessions. And let me see if this still works. Yes. So what I would like to do is something that all of you would think is considerably risky, and I do too, in fact. I'm scared to death. But what I would like to do is I'd like the conversation to happen out here. The rules are very simple. Anyone can ask a question, and anyone else can answer it. And the reason is because I know there are many more smarter people in this room than I am. Because what I'd like to do is I'd like to begin this conversation in this community about where do we go next in terms of completing this revolution that Leslie Lamport started for us. So who would like to go first?
So I know very little about like quantum physics at a robust level. But so the idea of entropy and then you have something happen and then unhappen, or like the pool ball example you gave, couldn't you actually tell because there's a loss of energy that happens? And so how do you think that applies to this reversible computing principle?
So I'm going to give you an example right now. So it turns out if you're an atom, and I'm an atom, unless we were two computers maybe, and I have a piece of information, okay? And if I give you that information, I no longer have it. But if you give it back to me, I now have it and you don't have it. So it turns out that this is what we call in physics, we call this shared information or mutual information. So between the two of us, we have this thing, but when you look at either one of us at a particular point in time, either you have it or I have it. But to the outside world, they have no idea. Well, let's imagine there's no light in this room, unless someone taps you on the shoulder and says, do you have it now? So it turns out that that's a model that kind of works. It has some mathematical similarities and some difficulties, but this idea that we can share something is an interesting one, and what we hear or is discussed right now in this physics community is that when I give you that, you are receiving information. What am I experiencing? I'm experiencing the loss of information, which is entropy.
Yeah.
So that's one of the ways that I look at entropy. I actually don't like that particular idea that entropy is involved. I like to think in terms of, subtracting and adding information, because if entropy is the opposite of information, then we should stop calling it entropy. And many years ago, when Shannon initially tried to name the concept he was coming up with in his mathematical theory of information, a very famous mathematician said to him, you should call it entropy, because first of all, it's got the same kind of characteristics of thermodynamic entropy, and nobody really understands what it is, so you'll have an advantage in an argument. Did I answer your question?
Yeah. I mean, so it's interesting. There's definitely like energy loss in the transmission of happen and unhappen, and like maybe if you would notice it from the whole system but couldn't determine. It also sort of sounds like for this to totally happen, we have to sort of basically embrace totally functional programming because you can't have side effects anymore.
Thank you. Anyone else? Now remember the rules though, I'm not going to answer every question. Anyone can answer the question that's been posed.
So if every instruction in a computer can be reversed, or wouldn't we have a perpetual computation machine, which basically takes no energy and computes everything?
Anyone want to have a go at that?
Just for fun. Everyone can argue back with me. So I would say that that's actually different layers of abstraction, right? If we have completely reversible computing at the layer of the software, that doesn't necessarily imply there's a physical layer that's energy free or not still moving forward in what we generally consider time, right? So I mean, it's sort of the same argument as we live in our entire universe is a simulation, right? It's just layers of abstraction.
Anyone else?
Another way to think of it, I would say, was you could think of each machine being a state machine, and therefore if you reverse the state in each machine, then the configuration is just being reversed to the same state it was before, so therefore there's zero energy change.
Here.
So I guess I'll respond and offer another question. So I think if you, unless you are thoroughly, sufficiently radically rethinking your hardware, you're going to end up consuming a lot more energy storing the history of everything you have to undo. That's going to be true for most hardware you have today. There's also some other things that you run into, like, well, sure, maybe fundamentally everything isn't simultaneous, but if you look at most parallel processors today, if you want to get a lot more performance from your computer, you need to do that by thinking about simultaneous parallelism, not just concurrency. Concurrency can let you scale out distributed, but if you want to take advantage of a GPU, you better be thinking about things actually happening in the same cycle, because there's instructions for that. So I guess that's the thing I go into. Especially there's the, Paul, I think, brought up these quote from the Maurice Herlihy and Nir Shavit book. That's a textbook on processor programming. If you want to be fast with that, having everything be asynchronous, in order to implement that on systems today would require using a lot of very expensive synchronization primitives, which you can avoid if you take advantage of knowing about locality or knowing about things like SIMD. So, I'd push back a little bit there. If this is such a fundamentally good idea, is this only a fundamentally good idea at the distributed level? Because just as somebody who spends a lot of time worrying about multi-core, SIMD, GPUs, things like HPC, which even their supercomputers, they build with a very different approach than a lot of the data centers that I think people would run various web services on. So they seem to not be entirely on board with this agenda.
So we were actually kind of thinking about a lot of the same things, and we've been talking about this offline prior. But you sort of started with, we need to radically change our hardware, and I think another thing that's kind of subtle here is the system model we work in either needs to radically change or matters greatly to this discussion, because that's kind of the difference there, right? Is what you're talking about is, in my system model of the world, or does it matter, and is it okay for me to adopt this one to accomplish my goals versus like in the distributed world? So I think to accomplish this reversible idea, it's less than fundamentally changing the hardware. We need to fundamentally change how we model our system model of the world, what happens. And so I guess, go ahead.
May I ask a question?
So,
okay. Okay, I was going to say I really like the problematization of time, making it something we think about, but at the same time, I was trained as an engineer and I really like error bounds and thinking about things as probability clouds. So, all the error could go in the corner of that room, but it's a very low probability. So it'd be really interesting to see if we're talking about improving NTP, we're getting better notions of one frame of reference predicting another frame of reference clock drift. Think about that as a model, right? How big is that probability distribution? And if we want to squeeze our error bounds to some defined quantity, how many errors are we willing to tolerate? And can we work in a framework where it's not just all crazy, right? Can we get some error bounds? If that makes sense.
So was that a question?
My question is, have you seen work, what are the error bounds as you start to get rid of the uniformity of space-time?
When it comes to network time protocol and PTP in particular, we don't know what they are, because what happens is the algorithm throws data away when it's beyond a certain bound. It assumes that the other clock is bad or there's something gone wrong or is a fault. That is the fundamental challenge to the assumption against, are we all living off a background of time which has a relationship across all of our machines. The original understanding of this, at least my original understanding, came from Leslie Lamport's paper. It came from his description of what causality was giving us, instead of this notion that we can have this common view of time. So perhaps this is a good point to interject. The conversation could continue as long as you would like. But just so that you all know that Leslie Lamport is actually in the audience here. So Leslie, if you'd like to raise your hand. So Leslie and I actually really didn't meet properly until this evening on the train on the way up. And now you know why I was so terrified and intimidated giving this paper. So let's continue with the questions. You can get as lively as you like, but let's have the rules be anyone can ask a question and anyone else can answer them.
So I just wanted to point out that, going back to the start of this thread of conversation, hardware actually is basically event-based already. You have various, if you peel back the layer of abstraction that's making it look synchronous, you've got signals triggering, events happening. Even if you look down to, you've got a clock which is just sending signals to other processes or other functional units, and then you actually have asynchronous hardware where, one register says, "Hey, I'm done this computation," and sends it off to the next, adder or whatever. So you basically have a graph of computations that get completed whenever they are done. And that's, I think, being explored for super low power usage. So microwatts, I think. I'm not too familiar with this.
So I'm going to take the implied question of that. One of the motivations for the Reversible Computing Conference is actually to take advantage of something called Landauer's principle, which basically says, at the deepest level in physics, energy is not dissipated unless information is erased. In other words, at the quantum level, there is no power dissipation. Until you actually take information and energy out of the system, it's an energy-free system. In other words, it's a conserved quantities system. One of the things that's starting to emerge is that this original emphasis on low-power computing, which is what the reversible computing community was looking for, is starting to move in the direction of, well, maybe we can use this reversible computing idea here for fixing faults more quickly and more deterministically in local places, rather than this big global idea of being able to build a reversible computer. Does anyone else want to take a crack at answering that question?
I think we probably have we're short on time, so who has 2 more questions? Okay, and then after that we can just continue this in the bar. You had one, right?
I'm really new to this, but the entanglement as a basis of something other than the current conception of space-time, is it something that can be intuitively grasped by someone who doesn't have in-depth training of this system?
Anyone want to take that question? Okay.
All right. I have it.
Okay.
Okay, maybe don't. No, yes, I do.
So full disclosure, I work for him. He's my boss, so I better be careful what I say.
I only hire people who are smarter than me, by the way.
Paul gave me the paper on this, and while I have an undergraduate physics degree, it was pretty flaky, but I was able to grasp the general concept that from outside of the system, there's no change. It's just fixed, right? And that it's only when you're in the entangled system that you see change. So there is no time except for the entanglement within the system. If you're outside the system, you can't be entangled with it. So I got that intuitive sense just from reading the first 2 pages of this paper, and the rest of it was way beyond my understanding.
So my instinct, I think, answering that question is, it's actually a lot easier to understand it in the new frame of reference, just like Copernican solar-centric universe was a lot simpler than the Earth-centric universe. Once we've grasped it all, once we've gone past this threshold of understanding it, we'll look back and say, why did we ever make everything so complicated? So to answer your question, your intuition has to be tuned into the new ideas before you suddenly see how it works. And I don't have a full vision of this, I have to admit. I don't have all the answers to anything. But my feeling already is that I can reach out and I can touch that intuition, and it feels much simpler than anything that we've done before.
I guess I've got kind of the opposite question here, which is that the opposite concern, which is that a lot of the examples here, 2 electrons, and what happens when there's billions of electrons that are entangling with each other, and you end up with a chaotic system that's very sensitive to its initial conditions. And things like, if you know what the logistic map looks like, the left side of the logistic map is very simple and you've got a few states, the right-hand side is incredibly complex. So for simple things, you can kind of maybe squint at it and figure out there's reversible things, but as it gets chaotic, is that reversible, or does it just get to be too hard at that point to make chaotic things with the very sensitive, with the initial conditions, make it totally chaotic, right?
Anyone want to try answering that question?
We have kidnapped the microphones.
You've kidnapped the microphones. Okay,
Yeah.
I'll have a go then to finish
Yes.
this up. So think of this as like I am drawing an analogy. When everything is a background, it's like there was a gas of particles, and you get into those situations which we call, statistical mechanics and chaotic systems and so on. But when you channel the energy and information in a very fine way between two monogamous entities, then you don't get that chaotic behavior. What you get is the ability to essentially do what's called the no cloning theorem, which is you can't copy a quantum state, but you can steal it. So my intuition is that if you channel your protocols down a wire, and that wire has a property of like in-order delivery, then you can do much more interesting things than we do today, trying to push packets over data center networks where they're like a gas of IP packets that can land anywhere at any time, and that can be drop delayed, duplicated, or reordered. So in other words, when we start thinking about things in this way, I think things become much simpler and very much more determinist, but only very locally, not on a global scale. But when you can do things in a provable way locally, you can compose that to do more interesting things globally. Did that answer your question? Thank you. All right, well, thank you very much, everyone. And I'd like to salute Leslie Lamport for his incredible gift that he's given us all in computer science. And I would like to see us all rise to the challenge of completing this revolution that he started with this paper 38 years ago, time clocks and the reordering. Time clocks and the ordering of events. Thank you.